So one of the things that really surprises me is I've had a large number of graduate students and postdocs, and they've all been brought up to believe that inflation just is. It's textbook physics. It's proven to exist. It's really part of the history of the universe. Now, this is very different from how I was brought up in, late 80s, early 90s, where inflation was still, was the most popular theory for the beginning of the universe, but it was one possibility, and there were other possibilities on the market. It was very speculative, but it was, a very promising speculation. Now, you have devoted a large part of your career working on inflation. Can you tell me a little bit about your background with regards to inflation, and what made you believe in it, and what was the intellectual atmosphere around the field when you were getting started?
Mm-hmm. So I was trained as a particle physicist. So since inflation is based on particle physics, this is the reason why I became interested in inflation. And I think for me the turning point was really the publication of the WMAP data, because this is the first time that we had the detection of these peaks in the CMB. Before that, as you very well know, there were competing models, like for instance topological defects, that do not predict these peaks, but just a bump in the power spectrum. So for me the turning point, and I think the reason why inflation has become so popular, is that we have these peaks, and inflation is the only way to explain those peaks. And the presence of those peaks ruled out those alternatives. So for me, the turning point was that, the detection. Or maybe you could argue that it came even before, because even with earlier experiments like
maximum boomerangs.
Exactly. So the rise of the first peak, maybe the second peak.
Yeah.
But with WMAP really came a clear detection of maybe the 2 or the 3 first peaks. So really for me this time period between boomerang and WMAP is really the turning point. It's really those measurements that convinced me, and I think the community, that inflation was on the right track.
Mm-hmm. And so when you were growing up, did you have a sense that there were competing models, that there were other alternatives, or did you have a sense that people were already locking on to inflation as?
No, when I did my PhD, really, I remember very clearly that topological defects were really considered as an alternative to inflation.
Tell us a little bit about. I did my PhD on topological defects,
so maybe you can explain.
Well, topological defect is a very elegant proposal that was ruled out exactly because of data like the maximum boomerang data in 2000 primarily. And it's the idea that at very early times, the universe underwent a phase transition. Underwent multiple phase transitions. And during these phase transitions, there were symmetry breaking patterns that could have led to the formation of topologically stable structures. That is, structures where the field is tied, the fields in the universe are tied up in knots. A classical example is monopoles, magnetic monopoles. You would form magnetic monopoles, but one of the most beautiful examples is the formation of cosmic strings, where you have lines of energy density, which would then evolve, collide with each other, and in some sense stir up structure. I think this is what you're talking about, topological
Absolutely.
defects. And the interesting thing about topological defects was it was uniquely predictive. Mm-hmm. Basically, you had one parameter, which was the symmetry breaking scale. Everything else was fixed. There was no spectral index. There was nothing. You just had to work out the dynamic. It was very difficult to work out because it was very nonlinear. And as you rightly point out, towards the end of the 90s, we began to make proper predictions, and it predicted no peaks, just predicted up and down. And what we saw with maximum boomerang is we saw the first peak and the second peak. So we saw very clear evidence for the acoustic peaks. And that was a beautiful example of a theory being falsified.
Absolutely.
Now, it's interesting that you react that way because I think there's more to it, though, because you say that you were educated in an environment where there were all these different theories, but it's only with WMAP that you said, okay, inflation was the thing. That's what did it for me with regards to inflation. I was brought up working on topological defects, and I have no doubt that topological defects were ruled out. And the data is remarkably consistent with inflation. And yet, I still find it difficult to see this as evidence for inflation. If anything, I see this as evidence that we haven't been clever enough in trying to figure out alternatives that will give us exactly that kind of structure, the peaks in the right places. Sure, inflation works, and by far, I would agree that at the moment, in my mind, it's the only compelling alternative. But I just think that we have focused too much on that one possibility and haven't really tried to explore and step back and figure out what are the essential properties of a theory of the initial universe that could lead us to this, which just shows how we all, we behave differently with regards to evidence. What would you say are the competitors at the moment, if you could call them that?
Yes, so I have worked myself on that,
on
bouncing models.
Tell us a little bit about bouncing models.
So a bouncing model is a model where initially you start with an infinite universe, then you have a phase of contraction, the universe reaches a minimal size, and then it expands again. In those models, people have shown that in the contracting phase, you can produce a power spectrum which is compatible with the data. So a priori, it's doing as well as inflation is doing. And therefore, this is an alternative to inflation. My problem with this type of models is the bounce itself. Because what people are doing usually is to calculate the power spectrum in the contracting phase. Then they assume that the power spectrum propagates through the bonds without being spectrally affected. And therefore, what they have computed in the contracting phase, they claim that this is what we should see in our expanding phase. And this I have hard time to believe it to be true. It may be true in some specific models, but I think it illustrates the difficulties of those models. Namely, we know that in order to produce a bounce, we have to go beyond general relativity, unless you assume there is curvature. But in general, you have to go beyond general relativity. So this is already something that you do not need to do for inflation. But why not? And then it becomes extremely complicated to calculate. So you have to choose a theory beyond general relativity, and then you have to really calculate the evolution of the fluctuations during the bonds, and this is extremely difficult. So it's a technical problem, of course. It's not a conceptual one. The conceptual one for me is that you have to go beyond general relativity, which is something that you do not need to do in the case of inflation. So
it's interesting you object to that, because you have to go beyond general relativity at very early times, in a very high energy regime. But we expect to go beyond general relativity. String theory tells us that we go beyond general relativity.
Yeah.
So
but I would say that inflation has nothing to do with that. Sometimes people say that a shortcoming of inflation is that it does not solve the initial singularity problem. And it's true, it's perfectly true. It does not solve the presence of a singularity, but I think it has nothing to do with inflation. Inflation is not designed for that. It's just a theory of what occurs around, let's say, the gut scale, the ground unified theory gut scale, and it's not designed to address what occurs at the Planck mass. So I would say it's an effective theory, valid at scales that are much below the. the Planck scale, and therefore inflation is not designed to solve the initial singularity problem.
I think we got a little bit sidetracked. Your objection to these bouncing models is that they invoke modifications of general relativity. And what I said was, well, but we expect modifications of general relativity at high energies. So that's not a huge demand for a bouncing universe.
No, but I agree with you. It's not a huge demand for...
In fact, it's inevitable.
Yes, but in some sense it means that it's more complicated or more ambitious,
sure.
if you wish. Yeah.
I think, but as long as...
In terms of effective field theory, inflation is a much more modest approach.
Yes. Yeah.
And it's sufficient. So I don't see why I should...
but that's really interesting. So, see, but I think that really gets to the core of the problem, which is, if one has found a theory which is good enough, should one stop? You know, which is kind of good enough, although, as you know, there are a lot of objections to inflation to do with fine-tuning, initial conditions, etc. But should one stop looking?
No, this is not what I am saying. I mean, if somebody comes with a theory which convinces me that it's doing better than inflation, then I would give up inflation, no problem.
Okay, so yeah.
It's just that because as I said before, I was trained in particle physics, in high energy physics. So I usually think in terms of effective field theory.
Tell me a little bit about what you mean by effective field theory.
So effective field theory is a way to understand particle physics which is very efficient, and basically it's telling us that in order to understand low energy physics, you don't need to understand what happens at high energy physics. So for instance, to understand the flow of a river, you don't need to understand quantum mechanics of the molecules that made up the fluid, for instance. So it's the same for inflation. Inflation is characterized by some energy scale. Usually also we don't know at which energy scale inflation occurred. But in many models of inflation, it occurred around 10 to the 15 GeV, so or 10 to the 16 GeV, so around the ground unified theory scale, the gut scale, and so a priori, the only thing I need to understand inflation and to design a model of inflation is to understand the physics at this scale. I don't need a priori. Also, it's true that for inflation there is a problem with respect to this question, but a priori, if I trust effective field theory, this means that I only need to understand particle physics at the gut scale and not particle physics at the Planck scale, for instance, in order to design a good model of inflation. While for bonds, I think that this would not be the case, because since by definition I go through this phase where I have all these corrections, it means that I cannot use effective field theory to characterize what occurs at the bonds. Of course, I can do it during the contraction phase or during the expanding phase, but at the bonds, I think there is a problem, simply because we go through a high curvature regime where all the corrections are important.
Interesting. You say all the corrections. Okay. You could imagine that there's another effective field theory which is valid in that regime, which you have to include more terms, but again you truncate it. But okay.
What I mean is that for a bond and for the calculation of the power spectrum, you really need to take into account those corrections.
I agree.
It's necessary.
I agree.
While maybe it's not necessary for inflation.
Yeah, I agree.
This is what I mean.